Hey, welcome back, you guys, to your favorite Calculus 2 class. So we've talked about parametric curves and parameterizing a curve, and now we're going to work with this concept with calculus. So we're going to do the calculus of parametric curves, okay? And you can read through this, in your own time, a little application, but we'll get to some problems here. So the parametric form of the derivative. So if x equals f of t, you've got your parametric curves here. Y is defined in terms of t as well. Then dy dx is dy dt over dx dt. Now dx dt cannot be 0. And you can read through that proof if you'd like to in your own time. So let's go ahead and run through this first one. Let's find the slope and the tangent line of the curve here. So number one, let's find the slope at t being pi. All right, so we need to find the derivative, of course, gives us our slope, right? Dy dx. So dy dx is defined as dy dt over dx dt. And so we're going to go to the side here and note we have x is 2 sine of 2t, and we have y being 3 sine of t. So dx dt would be, now we just take the derivative. Derivative constant stays there, derivative sine is a cosine. I got chain rule, derivative 2t is 2. So dx dt just ends up being 4 cosine of 2t. And then we find dy dt as well. 3 stays there, derivative sine is a cosine. And now let's throw that in. So dy dx is dy dt, which is 3 cosine t, over dx dt, 4 cosine 2t. And so that'll give us the slope, but we want the slope at t being pi. So let's throw pi in for t. 3 cosine pi, 4 cosine 2 pi. Well, we know the cosine of pi is -1. We know the cosine of 2 pi is 1, so we got -3/4. So the slope at t being pi is -3/4. There's our slope, right? Now we want to find the tangent line. The equation of the tangent line at t being pi. Well, we already have a slope, and so to write the equation, we need a point and a slope. So let's find the point. We know x of t is 2 sine of 2t. We know y of t is 3 sine of t. So let's plug in pi. We got sine of 2 pi is 0, so we got 0. So the x value of pi is 0. Let's find the y value of pi. Oops, that's sine of pi. We know the sine of pi is 0. So we get 0, y of pi is 0. So our point xy is 0, 0. That's our x and y when t is pi. And we have our slope we found was -3/4. So y minus y1, let's write the equation of the line, equation of the tangent line. So y minus 0 equals m x minus 0. So y equals -3/4 x. All right, this is a good you try it problem. So if you want to go ahead, pause the video, now would be a good time. All right, so we're going to find slope at t being 1, dy dx is dy dt over dx dt. I went to the side, I found dy dt, which is 2t. I found dx dt, which is just 6. So dy dx is t over 3. And I want the slope at t being 1. So I got t over 3, 1 over 3. So my slope is a third. I know my slope is a third. But I want the equation of the tangent line when t equals 1. So I got to find the x and y value when t is 1. So I have a point on this parametric curve. So x of 1 is 6 times 1. So my x value is 6. My y value is 5. So I have the point 6, 5, and my slope is a third. So y minus y1 equals m, x minus x1. So y minus 5 equals a third, x minus 6. Or if you want to expand that, y equals 1/3 x minus or plus 3. So either of those, that would work or that would work. Be the equations of that. And you know what? Let me give you a visual of this on Desmos. So we graph the parametric curve. The x was 6t, the y was t squared plus 4. T was all real numbers. Let's just go from like -9 to 9 so we get enough t values to kind of fill it up here. There's our curve, right? I did not eliminate the parameter, so I don't have the rectangular equation for that. So I'm just graphing it as a parametric curve. But let's put on, our point was at 6, 5. Let me label that point. There's our point. We want the equation through that, the equation of the tangent line, which ended up being y equals 1/3 x plus 3. So you can see that equation line going right through that 6, 5, right? That's the equation of that tangent line right there. So that's kind of a nice visual of that. So this is another U-try problem. You notice I wrote out dy dx. I found dx dt, dy dt. I'm going to throw those in. So dy dt is the secant squared. Dx dt is the secant tangent. So dy dx, one of those secants cancels. So we got secant over tangent, which is 1 over cosine. That's sine over cosine. So we end up with 1 over sine, or the cosecant of t. So dy dx is the cosecant of t. We wanted at t being pi fourths. So we got dy dx, t being pi fourths. So that's cosecant of pi fourths. That's 1 over sine pi fourths. In other words, 1 over root 2 over 2, which is 2 over root 2, which is 2 root 2 over 2, which is root 2. There's our slope. So our slope is root 2. We need the tangent line, so we need points. So we need x of pi fourths, which is the secant of pi fourths. We also need y of pi fourths, which is the tangent of pi fourths. Well, tangent pi fourths, sine pi fourths over cosine pi fourths, that's 1. Secant pi fourths, that's that 1 over cosine pi fourths, or that root 2. All right, 1 over root 2 over 2, which is root 2. So we have our root 2 comma 1, and we have our slope. And there's our equation, or add 1. Either of those is fine. The equation of the tangent line. Before I get into this question here, we're given the position of an object at time t, given by the set of parametric equations, and I want to kind of get a feel for this. If I plug a few points in here for t, if I let t be 0, x would be 0, y would be 1. If I let t be 1, I get x would be 7, y would be 4, and eventually I definitely want to do it for t being 2 here. So that would give me 22, it would give me 13. Let me do one more here. 3 would give us 45, 28. So if you were to graph this with decimals or whatever, you get kind of look at this thing. Let me see if I can do my best to graph this. And so we got 0, 1, we got 7, 4, 22, 13. Anyways, it kind of starts out like this, and then I didn't do the greatest. You can look at your graph online if you want, but anyways, it's kind of like that. Part A says find the horizontal velocity. So the horizontal vector represents the horizontal velocity at t being 2, right? So at this 22, here's this 2213 point. Whoops. 2213 point. So I'm trying to find this horizontal vector, okay? And so what I do is I'm going to take x of t, which is 4t squared plus 3t. I'm going to go ahead and find dx dt, or x prime of t. So we got 8t plus 3. And I want it at the moment that t is 2 seconds. So x prime of 2 . So we got 19. So this is 19. If you want, you could throw on. The original is in meters, so this would be meters per second. So this is representing this horizontal vector is 19 meters per second. So the length of this is representing like how fast it's going, right? Longer length, faster it's going. If you're thinking back to your vectors from your trigonometry course. Let's do part B. So the vertical velocity, take the y value. So y of t equals 3t squared plus 1. So y prime of t equals 6t. We want it at the time of 2. So we got 12 meters per second. Okay, so the vertical vector is up 12 meters per second. Okay. And I could also draw this horizontal one up here if you wanted to as well, right? All right, so part C on this is saying we want the speed at the moment t equals 2, okay? So speed is the magnitude of the velocity vector. Well, the velocity vector is the sum of the horizontal and vertical components. Let me write that down. Speed is the magnitude of the velocity vector. The velocity vector is the sum of the horizontal and vertical vectors. Their components, right? So let me draw this. Let me do it in orange here. So if you remember, if you have a vector u plus vector v, the sum of those, it goes from the initial to the terminal. That's vector u plus vector v, right? And so that's what I have here. Let me draw it in orange right here. That's the velocity vector there in orange that I'm looking for. Okay, and so this speed is just the magnitude of that. So the speed, so what's the length of that? Well, a squared plus b squared equals c squared, right? And so we got square root of 144, it's going to t squared. You punch that in and you get 505. And by the way, this is the speed when t equals 2. So this will be, punch that in, 22 point, let's see here, 4722050542 meters per second. So it's about 22.5 meters per second. That's this orange one right there, right? That's your speed when t equals 2. Well, let's go ahead and find the points on the curve that have a horizontal tangent line. So I don't know what this thing looks like, but we're looking for where does it have a horizontal tangent line? Well, the slope would be 0, right? And where would it have a vertical tangent line? I didn't do that very good. And where would you have a vertical tangent line? Then your slope would be undefined, right? Vertical line has a slope that's undefined. So visually, that's what's going on. We're just solving this thing algebraically. Let's do the horizontal tangent first. When does it have a slope that's 0? So we need dy dx. All right. Well, we know dy dx is dy dt over dx dt. Well, we have y is t cubed minus 3t. So we know dy dt is 3t squared minus 3. We also have x being t squared minus t plus 2. So dx dt is 2t minus 1. So let's throw those in. I got 3t squared minus 3t squared minus 3 over 2t minus 1. And this needs to be, so here's dy dx. This got to be 0, right? I need to have a slope that's 0. That means my numerator's got to be 0, right? 0 divided by anything, 0. So that means 0's got to be 3t squared minus 3. So 3t squared equals 3. T squared equals 1. T is plus or minus 1. So if t is 1, let me find the x and y values there. So x of 1 be 1 squared minus 1 plus 2. So x of 1 would be 2. Y of 1 would be 1 cubed minus 3 times 1. So we got negative 2. So I got 2, negative 2 is one of my horizontal tangents. So I have a horizontal tangent at the point 2, negative 2. That's where I would have a slope of 0. We also have to account for t being negative 1. So x of negative 1 be negative 1 squared minus a negative 1 plus 2. So that ends up being 4. Y of negative 1 is negative 1 cubed minus 3 times negative 1. I get negative 1 plus 3, so I get 2. So I have a horizontal tangent at 4, 2 as well. So there's my 2 points where I have a horizontal tangent. Now let's address the vertical tangent. Vertical line has a slope is undefined. All right, so we had dy dx, which was 3t squared minus 3 over 2t minus 1. This has got to be undefined. That means the denominator's got to be 0, right? I can't divide by 0. So the question is, where does 2t minus 1 equal 0? Well, that'd be when t is a half. And so we just got to throw in t being a half. T being a half. So x of t equals t squared minus t plus 2. There's a 2 up there. So we get 7/4. Y of t was t cubed minus 3t. So we got negative 11/8. So we have a vertical tangent at 7/4 negative 11/8. Well, the second derivative, if you remember, dy dx is, we're taking the derivative of y with respect to x on the left, derivative of y with respect to t over to the derivative of x with respect to t, right? So we have this dy dx is ddxy over ddty dx dt. So if we take the derivative, then wherever we have the y on both sides, we can replace it with dy dx, right? So we replace that with the dy dx, and that'll leave us with this second derivative. So the second derivative is d dt of dy dx over dx dt. So that's the equation that we're going to use to run the second derivative here. So when we're finding, we got to find both the first derivative. Let's go ahead and find that first, and then we'll use that equation to find the second derivative. So we have x is t minus t squared. We got y is t minus t cubed. So dx dt is 1 minus 2t. Dy dt is 1 minus 3t squared. So dy dx is 1 minus 3t squared over 1 minus 2t. Okay, there's our dy dx. Now, the part B, the second derivative is d dt of dy dx over dx dt. So this is the second derivative for a parametric equation. And so the second derivative will be d dt of dy dx. Well, dy dx is 1 minus 3t squared over 1 minus 2t. And this is all over our dx dt. Well, we know dx dt is just 1 minus 2t. And so our second derivative will be, we're going to use the quotient rule on this, right? So I take the derivative at the top. This is how I remember derivative at the top, times the bottom, minus the top, derivative of the bottom, all over bottom, squared. And this is still all over dx dt. And so when I put that over 1 multiplied by the reciprocal, I'll just have this top. Let me go ahead and distribute that through. Negative 6t plus 12t squared. And I have a positive 2 that I'm distributing through. So that's 2 minus 6t squared. This is all over 1 minus 2t to the third. And so I've got, let me combine like terms here. Second derivative is 6t squared minus 6t plus 2 over 1 minus 2t cubed. And there's our second derivative. All right, this next one's good. You try a problem. I kind of jumped a little bit ahead here before I recorded, but good time to pause it and try this thing. I've got dy dx is dy dt, which is 2 in this case, over dx dt, which is 2t. So our dy dx, 2 over 2t is just a 1 over t. There's the first part. Now let's find the second derivative. which is d dt dy dx over dx dt. And so our second derivative is the derivative with respect to t of dy dx. Well, dy dx was 1 over t. And then this is all over dx dt. Well, we know dx dt was 2t. And so the second derivative, let's take the derivative of t to the negative 1, right? Taking the derivative of t to the negative 1. So negative 1 t to the negative 2. This is all over 2t. And so the second derivative is negative 1 over 2t, and I've got a t squared down with it. So I got down here. Here's our second derivative. Here we're going to be asked about concavity. If you remember from your first calculus course, first derivative would tell you about the functions increasing or decreasing, right? Second derivative is telling you about the concavity of the function. So we're going to need to find the second derivative. So let's go ahead and find the first derivative. And if you notice, dx dt would be 2t. So this would become 2t plus 3t squared dy dt over dx dt, which is 2t. And so dy dx, that's 2t over 2t, so 1 plus 3t squared over 2t, so that's 3t over 2, or 3 halves t. So 1 plus 3 halves t. So that's the first derivative. We're being asked about concavity, so we're going to find the second derivative. So d dt dy dx over dx dt. So second derivative here would be derivative of the 1 plus 3 halves t over dx dt here is just a 2t. So our second derivative of 1 plus 3 halves t is just a 3 halves over 2t. So our second derivative is 3 over 4t. Now we want to know where this thing is concave up or concave down, right? So where are the critical points? Well, if t is 0, that's a critical point when we're testing this on our second derivative test, right? So we're testing around t being 0 here. So if I throw in like t being negative 1 into my second derivative, I got 3 over 4 times negative 1. Well, that's negative. It's a negative value. So it's concave down to the left of a t being 0. Now I throw in like a t being 1. So 3 over 4 times 1, that's positive. So it's going to be concave up, right? Concave down on the left of t being 0. So let's go ahead and write that down. We're concave up for t being positive, or if you want to do it in interval notation from t being 0 on, or concave down for this parametric curve when t is less than 0, or t values from negative infinity up to 0. That's your concavity.